In section 6.5, we'll introduce the concept of specific heat, the heat required to change the temperature of a substance. We'll define specific heat and the mathematical equation used in calculating it. Let's begin. The amount of heat needed to change the temperature of a substance is Q equals mc delta T, where m is the mass, c is the specific heat, and delta T is the temperature change calculated as final temperature minus initial temperature. Since the Celsius and Kelvin temperature scales are offset by a constant factor, the difference between two temperatures measured in Celsius or two temperatures measured in Kelvin will be the same. The specific heat, C, is the number of joules required to raise the temperature on 1 gram of the substance by exactly 1 degree Celsius or Kelvin. Units of specific heat are in joules, gram, degree, Celsius. Notice that this equation only holds in the absence of a phase change. Moving from a solid to a liquid or a gas requires a different heat calculation. It's helpful to understand the physical difference between a substance with a low specific heat compared to one with a higher specific heat. Take sand and water, for example. The specific heat of dry sand, composed mainly of silicon dioxide, is about 1 joule per gram degree Celsius. Dry sand on a beach can be uncomfortably hot to walk on barefoot during a summer afternoon. Water has a specific heat capacity roughly 4 times that of sand, so the water can absorb a significant amount of heat without experiencing an increase in temperature, so the water will still feel cool to the touch compared to the sand. What is the specific heat of liquid water? We can calculate it using the data provided and the equation Q equals mc delta T. Matching variables to numbers with their respective units, we see Q is 83.68 joules, delta T is 5 degrees Celsius, and the mass of water is 4 grams. Solving for C, we get C equals 4.184 joules per gram degrees Celsius. Here's one for you to try. How much heat energy is required to raise the temperature of 5 grams of ice by 5 degrees Celsius? The specific heat of ice, solid water, is 2 joules per gram degrees Celsius. First, match the variables to the information given. Solving for Q, we get 50 joules. Here's one that is a little more involved. Find the final temperature after 1,485 joules of energy is added to 16.7 grams of water, initially at 23.4 degrees Celsius. This means we'll need to take Q equals mc delta T and rearrange to solve for the temperature change. Delta T equals Q over mc. Plug in your numbers, making sure that the units cancel. Now determine the final temperature. When a solution is formed from the mixing of a solute with a solvent, the process can be endothermic or exothermic, depending on the identity of the solute, amount of solute, and mass of water in the solution. Let's work through an example to demonstrate. What is the enthalpy change for an acid-base neutralization that increases the temperature of 20 grams of solution by 10 degrees Celsius? Use the specific heat of water as approximately 4 joules per gram degree Celsius. Running through the calculation, we get Q equals mc delta T equals 20 grams times 4 joules gram degree Celsius times 10 degrees Celsius equals 800 joules. For the sign, we must consider that the temperature is increasing, meaning that the system would feel warm to the touch, which is typical of an exothermic reaction. The heat you feel is the heat moving from the system to the surroundings. If you'd like additional practice, consider working with the endothermic and exothermic reactions lab activity in Figure 6.9. As always, I'll leave you with the parting thoughts of the authors.